Okay, so we'll be continuing on our last topic of the discussion on magnetism and the magnetic force and the magnetic field. So today's discussion would be on motion of charged particles in a magnetic field. Okay, so the motion of charged particles under the action of a magnetic field alone is always motion with constant speed. Okay, so what is meant by motion with constant speed is that the particle that experiences the force produces a motion that does not accelerate. So there is no acceleration whatsoever. Okay, so in this illustration, what we see here is that we have a charged particle that is within a given region of a magnetic field. As we can see, if the charged particle is acted only by the magnetic field alone, the magnetic force causes the charged particle to move in a circular path. So let us try to analyze what is happening here. Okay, so what you see here in as the symbols as x's, this is the established direction for the magnetic field. Okay, so currently the direction of the magnetic field as indicated by these x's is directed into the screen. So the direction is from the outside of the screen going inwards into the screen of your computer. Or for example, if you're seeing this in front of the as a printed copy, and this supposed to be the whole page of the printed copy, so the direction of the axis here as the direction of the magnetic field points towards the direction into the page. Okay, so why is it that we symbolize the direction of the magnetic field this way? Okay, so try to imagine, for example, an arrow. So, for example, this arrow here. Of course, a usual arrow is has a tip which is pointed at. An arrow has a pointed tip. So, if you're going to look at the pointed tip of the arrow, what you are going to see head on would be simply a point. Whereas if you're going to look at the arrow at its behind or at the back of the arrow, what you will see is that the arrow has this arrow fly. So the arrow fly, just like the ones attached to a dart, if you're familiar with the dart pin that we use as a dart pins. So the dart pin has this fly behind the end of the arrow. So if you're going to look at the dart pin behind the arrow, you will actually see the figure of the fly in the form of an X. So this means that what we are seeing here as the direction of the magnetic field, where we are actually looking at the back end of the of arrows. So that this means that the arrows are directed into the page of or into the screen of this computer. Now, in the opposite sense, for example, if the direction of the magnetic field is out of the page, so instead of seeing x's as the direction of the magnetic field, what we are going to see is the tip of the arrow. So in replacement of the x's, we will be seeing, or the diagram would actually show that the magnetic field is represented by points that are directed out of the page or out of the screen. Okay, so that is the sign convention for the direction of the magnetic field in terms of arrows. Okay, so um, we have established the direction of the magnetic field in this diagram as directed into the page. Now let us try to see what is happening here. So what we see here is that we have a positively charged particle that enters the region of the magnetic field. So for example, if this particle started its entrance within the magnetic field at this point, so the direction of the velocity would be directed here as indicated by the green arrow. Now, just like what was presented earlier in the first video lecture of this series, we have discussed the relationship between F V, and magnetic field, as indicated by the formula F is equal to Q times V times B. And we also made use of the right hand rule or the left hand rule depending on the sign of the charge. For positively charged particles, we will be using the right hand rule. If the charged particle entering the magnetic field is negative, that means we'll be using the left hand rule. So, in our discussion of the motion of charged particles, what we see here is that we are given the magnetic field inwards, and the direction of the sign of the charged particle is positive. So therefore, we will be using our right hand rule to indicate the direction of the magnetic force. The direction of the force, although it's already indicated here that the direction of the magnetic force is upward at this point, going inwards to this direction at this point, going to this direction at this point. Now the point here is for you to practice the right hand rule. Okay, so if you're going to let us go through again with the right hand rule. Okay, so the right hand rule states that the direction of the forefinger should be pointed towards the direction of the velocity. So if you're going to do that, you try to point the four fingers towards this direction. Now, after which you will be doing the curling motion or the grabbing motion within an angle that is the smaller angle between the velocity and the magnetic field. Now, the magnetic field is directed inwards into the board or into the screen. So if you're going to do the curling and grabbing motion from the velocity towards the direction of the magnetic field towards that direction into the page of the screen, what happens to your thumb is that the thumb will be pointing towards the upward direction. Try to verify this using the right hand rule, doing the right hand rule on your own. Okay, so this should guide you with the direction of the magnetic force. So what happens now here is that the magnetic force would cause a deflection of your charged particles, deviating it from its original path. Now, the original path is, of course, the charged particle is originally moving towards this direction, as indicated by its velocity. Now, what happens here is if you have a magnetic force that deflects it towards this direction, a combination of the movement which is horizontal and the effect of the force which is vertical at this point would cause the charge to move this way towards this diagonal. Try to imagine, for example, if this is a person and the person the person is running towards this direction, and suddenly another person bumps into him towards this direction. So in effect, the person would actually move towards a diagonal direction due to the combination of the effect of the person's forward motion and vertical motion. So just like that is the same as what is happening here. The effect of the force combined with its original direction of motion would cause the charged particle to move in this direction. And this means eventually the charged particle would end up at a later position, which is probably at this point. Now, if once that the charged particle is already at this point, what happens is that its velocity would be directed now, instead of its original forward motion towards this direction, it would be directed towards this direction. And notice that since the force is applied perpendicular to the velocity, the acceleration produced by this force does not cause any change in the velocity of the charged particle along this direction. Remember your physics 1, that by virtue of Newton's second law, for the application of the force for every given mass of an object, the force causes an acceleration or a change in velocity of that object. for the given condition that when you apply a force, it should be in the same direction as the acceleration. So this means if you're going to change the velocity of this charged particle, in order to change the value of this velocity, you should apply the force in the same direction or in the opposite direction of this velocity. But since the application of the force here is perpendicular, this means that the acceleration produced by this force does not affect the value of the velocity. So therefore, although this force causes the charged particle to be deflected towards this direction, it simply changes its direction, but it doesn't change the magnitude of the velocity. Okay, so that is why what is stated here earlier in this statement is that motion of charged particles under the action of the magnetic field alone is always motion with constant speed, primarily because the application of the force is perpendicular to the direction of the velocity. So it doesn't the magnetic field doesn't change the speed of the particle. It simply changes the direction of the velocity. Okay, now of course if we're going to go back to our discussion on the electric field. Now the electric field is the type of field wherein when the electric field applies its electric force on the charged particle, the electric field could cause our charged particle to accelerate, simply because the application of the electric force by the electric field. The application of the force could be in the same direction of the velocity or in opposite direction. So this means that the charged particle could either be sped up or it could be slowed down, depending on whether the force applied by the electric field is in the same direction as the velocity or in opposite direction. Now, remember, what I'm discussing here at the moment is the effect of the electric field, but what is stated here is the application of the magnetic field. So make sure that you make the distinction between the two. The electric field could cause the charged particle to accelerate or decelerate, while the magnetic field cannot change the magnitude of the speed. It could only deflect the charged particle in terms of its direction. Now, if you're not able to get the concept, probably you could go back to our previous video lectures on our discussion on the electric field. Okay, so let's continue here. Now, once that the charged particle arrive at this location where it was deflected, what happens as a continuation is, of course, the application of the force by the magnetic field is always continuous. So this means all the time, the force is being applied on the charged particle every time that it moves at any location. So at this location, still that amount of force is applied on the charge by the magnetic field. But this time, of course, the direction of the velocity is towards this direction and not this direction anymore. It would be it is deflected towards this direction. So in effect, the combined effect of the acceleration due to this force and the direction of this velocity would deflect the charge towards this diagonal here, although it is no longer indicated here. So this means if you're going to continue with this pattern, eventually we would realize that the actual movement of the charged particle along the magnetic field or within the magnetic field, it would be tracing this circular path. So this means that the motion of charged particles within a magnetic field is always motion with constant speed along a circular path or circular motion. The charge moving at right angles at a uniform magnetic field moves in a circle at constant speed because F and V are always perpendicular to each other. Of course, what we see of course, just like any the concept of the circle, just like what is the concept of the circle, a circle has its radius, a circle has its circumference. So the next obvious thing to analyze here is that what is the relationship between the strength of the magnetic field, the velocity of the charge, the sign of the charge, to the shape of your circle. Does the strength of the magnetic field, the velocity, and the magnetic deflecting force affect the size of the circle? So let's try to explore that one. Okay, so now from our previous video lecture, we already established that the magnetic force applied by the magnetic field on a charge entering the field is given by Q times V times B. So this is the charge of the particle. So regardless whether the particle is positive or negative, so the V here is the velocity of the charged particle moving within the magnetic field. Of course, B is the magnetic field strength. Now, remember in your physics 1 that an object that is moving along a circle, of course, follows the rules of circular motion. Now, just like what was discussed to you during your physics 1, that in order for an object to move along a circle, there should be what we call a centripetal force, which causes it to move along the circle and is directed towards the center of the circle. And in this motion of charged particles along the magnetic field, the centripetal force is obviously the magnetic force exerted by the magnetic field on our charged particle. So this force actually is our centripetal force. And of course, the centripetal force, if you're going to review your physics 1, the centripetal force is actually given by this formula, m times v squared over r. Notice the form of this formula. This is m times v squared over r, m times a. Remember in your Newton's second law, F is equal to mass times acceleration. So if this is F, this is m. Therefore, v squared over r is your a, or your acceleration. So basically, our v squared over r is our centripetal acceleration if F here is our centripetal force. So what does this relationship tells us? It tells us that F is proportional to m, F is proportional to v square, F is inversely proportional to r, F is proportional to q, to v, and to b. Okay? And also between this form of the equation and this one, of course, F is equal to this, F is also equal to this, therefore this one is also equal to this one. So let us try to establish the relationship among the variables here. Okay, so first let's have the charge. Okay, the charge actually is in absolute value, so regardless of the charge, well, whether it is positive or negative, for a certain amount of charge and for a given velocity, that means the size of the circle would be inversely proportional to it, but the size of the circle does not directly related to q, because q is in absolute value. So what is affected only by the in terms of tracing the circle is the sign of the charge. So in our illustration here, the given sign of the charge is positive. So what happens to our circle is that the charge traces the circle in a counterclockwise motion. Now, if we're going to change the sign of the circle, having this as negative, what happens to our circle is our circle, it would be traced by the movement of the negatively charged particle in a clockwise direction. Okay? Now, what about V? Now, V is inversely proportional to R, so that means the greater the velocity, the smaller the size of the circle, as indicated by our r. Okay, so that's the relationship between V and r. Okay, so for the magnetic field is of course is related to V. The greater the magnetic field, the greater the magnetic force to be deflected. So this means the greater your acceleration of the greater the F, the greater the acceleration. Okay, so moving on. Okay, so solving for R from this form of the equations, if we try to solve for R, we have the relationship M times V over Q times B. Now, this establishes the relationship among the variables R, M times V, Q, and B. This indicates that R is proportional to M times V. This means the greater the speed of our object, the greater the size of the circle. The R is inversely proportional to the magnetic field. This means that the stronger the magnetic field, the smaller the R. Now, from here, let us try to focus on our V here. The angular speed omega, this is the Greek letter, small letter omega, of the particle can be found in the equation V is equal to R omega. So where does this equation come from? This is from your equation from your physics 1 regarding circular motion. Okay, so this establishes the relationship of what we call the tangential velocity and the angular velocity. The angular velocity, the tangential velocity is this velocity. It is the velocity tangent to our circle. Now, the angular velocity is the speed of the object around the circle. So the relationship between this linear angular velocity, this linear tangential velocity, and the speed around the circle, which is the angular velocity, is established by this equation, which is connected by the radius of the circle. Okay, so this is your linear velocity, this is your angular velocity. This is the tangential velocity, this is the velocity around the circle. Okay, so if we're going to combine this formula with this one, we could actually solve for the angular velocity, which results into V over R. If you're going to replace V in this equation, so this becomes, and solving for omega, of course, if we're going to replace V here by R omega, this becomes M R omega over Q times B, cancel R, so that becomes 1, cross multiply. We solve for omega, that becomes V, omega, it becomes Q times B over M. Of course, in circular motion, our omega is defined as 2 pi times the frequency F. Okay, so from this equation actually relates the idea of the strength of the magnetic field with what we call the omega, or the angular velocity. Now, in terms of application, the angular velocity is actually referred to in many applications as the angular frequency. Now, the relevance of discussing this angular frequency is that the angular frequency is actually related to the strength of the magnetic field in applications such as radio broadcasting. If you're going to if you're familiar with the DJs announcing in radios, announcing their station ID, such as, for example, 102.7. 102.7 refers to the angular velocity of broadcast of that radio station, and it is actually a number which is expressed as a value of your angular velocity or your angular frequency. And that is actually related to the strength of the magnetic field used to produce that amount of frequency, basically for broadcast purposes. So, for example, in a broadcasting tower of a radio station, they are broadcasting at a given frequency, for example, 10,000 kilohertz. So that number kilohertz is actually this value, which is the angular velocity or the angular frequency in broadcasting applications. That number in their station ID is actually this number, and that number is actually produced by a machine that produces a magnetic field strength that will produce that certain amount of radio broadcast or radio frequency. And of course, in circular motion, this is indicated by this relationship also, omega is equal to 2 pi times f. Okay, so let's take up one example for this one. Now, what we see here in this problem is we are introduced to a magnetron. Now, a magnetron is a device within a device that produces electromagnetic radiation, such as a broadcasting tower or a microwave oven or a radio tower and so on, or an X-ray machine. So any machine that makes use of electromagnetic radiation in order to produce electromagnetic waves. Now, in this example, a magnetron is used on a small scale, producing electromagnetic wave in the microwave bandwidth. Okay, so a magnetron in a microwave oven emits electromagnetic waves with a frequency of 2450 megahertz. So this is megahertz. So the question is, what magnetic field strength is required for electrons to move in a circular path with this frequency? Okay, so let's try to compute for this one. Okay, so this is the same problem as what we saw in the PowerPoint presentation. Okay, so from our set of equations, what we see here is that we have omega as equal to 2 pi f, which means that we are given the frequency of the magnetron or the microwave radiation, that is equal to, given this formula, we should be be able to compute for our angular frequency or angular velocity. So from there, we could actually compute for the magnetic field by deriving B from this equation. Okay, so having that, we will now have 2 pi f is equal to q times b times m. Solving for b, b would be equal to 2 pi f times m. Okay, so let me modify this first. Okay, so what happens here if we have 2 pi times f times m over q. Okay, so solving for b, we now have. Okay, so I encouraging everybody to do the same derivation, verify this on your own, and try to make use of your calculators in order to verify if the answer is correct. So our answer here is given in the scientific calculator as 160 or 60.8 Tesla. Okay, so of course, we are given the angular velocity as 2 pi f. We are given f, that is equal to 2,450 megahertz. Megahertz means 1 million. So this means if you're going to express 2,450 megahertz in scientific notation, this becomes 2.450 times 10 to the 9 hertz. Okay, so times 2 pi times. So what is this value? What is this 1.6? Okay, so let me correct this first. Okay, so what I'm doing is that I'm just modifying the givens givens in the problem. Okay, so it is stated in the problem here that the magnet what is being asked here is the magnetic field strength required for electrons. Okay, so it is given here that we have electrons. So just like what we have discussed early on in our introduction in physics 1, the electron has the charge 1.6 to the negative 19 coulombs, and for your information or for the information of everybody, the mass of an electron is a constant, and this is a known constant in physics and in science. You could look for the mass of the electron. You could Google it, and I am expecting that you will be getting the results as 9.11 to the negative 31 kilograms. Okay, so this is the workable value for the mass of the electron. Okay, so this remember this is a constant. Okay, so in our formula, so if we're going to plug in those values, so we have the value for the frequency. Okay, so times 2 pi times the mass of the electron divided by the charge of the electron. Okay, so if we're going to do the computation again, okay, so this is 2 pi. I'm expecting everybody to verify this also using your own scientific calculators. Okay, so 2.450 exp9 times the mass of the electron 9.11 exp negative 31 divided by 1.6 exp negative 19. Okay, so let me try that again. 2.450 exp9 times 9.11 exp negative 31 over 1.6 exp negative 19. Okay, so the answer is actually 0.0876 Tesla. Okay, so this is the strength of the magnetic field produced by the magnetron in a microwave oven. Now, comparing this with the magnetic field strength perhaps in producing electromagnetic radiations used for radio broadcast, this is comparatively speaking is very small. Of course, in our radio broadcast, for the purpose of our radio broadcast is to send radio signals from the source, and normally the waves produced by this magnetic field for its application should reach distances that are expressed in miles or in kilometers. Just like the AM station, if you're familiar with it, the AM station, just like, for example, DZBB, the radio broadcast of an AM station, for example, DZBB is located in Manila, but the radio broadcast for DZBB actually reaches even up to the south part of Mindanao. So try to imagine how much electromagnetic strength of the magnetic field that is used in order to produce such electromagnetic wave that would reach long distances. Now compare that with a microwave oven. A microwave oven is simply a box. Now, of course, the magnetic wave that is produced is confined within that box, and in terms of the strength of the magnetic field, it would be, comparatively speaking, would be very much weaker as compared to the ones used probably in radio broadcasting. Okay? Now, of course, I'll be leaving you much of your exploration of physics 2 with this last topic. Actually, this is our last topic. I will be finishing our discussion on physics 2, and I hope that you have learned the very basic principles of electricity and magnetism, and I'll just be leaving you further explorations for your curiosity to satisfy your own curiosity, and I hope you have appreciated your this study and your exploration of physics 2. And as for now, good luck to everyone in your exams, and have a good day.